Module 2, Lecture A, Lists and Tuples. By the end of this lecture, you will be able to create lists and tuples that represent ordered industrial engineering data, access, update, and summarize sequence data using indexing and built-in functions, and choose between mutable and immutable sequences for appropriate engineering records. Ordered industrial data, creating ordered records. In industrial engineering, the order of data points often matters because it represents the order of operations, events, or checks. Ordered collections such as lists and tuples preserve this sequence, making them useful for workflows, time-based measurements, priorities, routes, and inspection records. In these cases, each position in the data carries meaning, so keeping the original order helps accurately describe the process. When organizing ordered records, each position should have a clear meaning, such as time, movement, priority, or sequence. This makes patterns easier to interpret, whether tracking machine cycles, warehouse travel, or maintenance tasks. Well-ordered data supports clearer comparison and better decision-making. An effective ordered record must be consistent and match the engineering context it represents. Entries should use the same time interval or level of detail, so comparisons and analysis remain valid. This structure helps engineers and analysts communicate clearly by turning real-world activities into meaningful, organized data. Python code, creating ordered records. Ordered records help keep industrial data meaningful. Lists are used for changeable sequences of observations, while tuples are used for fixed sequences of facts. A workstation route list represents the ordered path a part follows through production, moving through cutting, drilling, inspection, and packing. Using a list keeps these operations in sequence and makes individual steps easy to access or change. A list is created to store hourly production counts for 4 consecutive hours, 42, 45, 43, and 47 units. This makes it easy to track production over time and update the values if the data changes. A tuple is used to create a fixed part record with a part identifier, production line, measurement value, and unit. Because tuples are immutable, the record cannot be changed after it is created. This helps protect constant data, such as part specifications or identifiers, and supports data integrity throughout the program. Use the print function to display the workstation route as an ordered sequence of operations. This makes the workflow easier to understand and helps confirm that each step is followed in the correct order. The first and last steps of the workstation route are printed to check the route sequence. The first item is retrieved using index 0, and the final item is retrieved with negative indexing, which avoids needing to know the list length. To summarize hourly output, add all hourly values to find the total production. Then, divide that total by the number of hours recorded to get the average output per hour. The output first shows the hourly production counts to give a quick view of performance over time. It then shows the total produced during the period, followed by the average output per hour, which summarizes the typical production rate. The third hourly output value is updated to 44 by changing the item at index 2, because Python lists start counting from 0. This shows that lists can be modified after they are created, unlike tuples, which cannot be changed. The update keeps the data accurate for that hour. We print the updated hourly output counts to review the corrected production sequence. This confirms that the data includes the latest adjustments and is accurate. The code displays a fixed part record stored as a tuple. The tuple holds key details such as the part identifier, production line, size, and measurement unit. Because tuples cannot be changed, the record stays consistent, and printing it makes the details easy to check. This script shows how lists and tuples can organize industrial production data. Lists store workstation steps and hourly output, allowing the program to display the process, calculate total and average production, and correct an hourly count. A tuple stores a fixed part record that does not change, highlighting the difference between mutable lists and immutable tuples. Recording ordered data. In industrial data, the order of values can be just as important as the values themselves. Cycle times, inspection results, and part measurements are easier to interpret when each value stays in its intended position. Lists and tuples are useful for this because they preserve the sequence of data, making them well-suited for ordered observations. Recording data in a consistent order keeps observations comparable and easier to interpret. Whether logging product measurements, following warehouse tasks, or reviewing sensor readings over time, the sequence preserves the meaning of the data and supports reliable analysis. When organizing ordered industrial data, choose the structure based on whether the sequence changes. Use a list for changing data, such as production counts or queue lengths, and a tuple for fixed data, such as machine coordinates or component dimensions. This keeps data predictable and easier to communicate, supporting better process analysis and operational improvement. Python code, recording ordered data. Lists are useful for ordered observations that may change over time, while tuples are better for fixed, structured engineering records. The key idea is to choose the sequence type based on whether the data needs to remain flexible or stay constant. Create a list to store the process cycle times in the order they were observed. A list works well because it preserves sequence and can be updated as new measurements arrive. The starting observations are 42.5, 41.8, 43.2, and 42.1 seconds. A tuple is being used to store a fixed record for a part. It contains the part ID followed by 3 decimal values for the part's length, width, and height in centimeters. Because tuples are not meant to be changed, this is a good way to represent stable part specifications. Use zero-based indexing to get the first item in a list, which gives the earliest recorded cycle time. Use negative indexing to get the last item, which gives the most recent cycle time without needing to know how long the list is. Add the new cycle time observation to the end of the existing list using the append method. Then find the average by adding all cycle times and dividing by the number of observations. This mean value summarizes overall cycle time performance and helps show the general trend. To summarize the cycle times, use the minimum function to find the fastest cycle and the maximum function to find the slowest. Together, these values show the range of observed cycle times. The cycle time data is summarized by showing the recorded observations, noting the first and last values, and calculating the average time rounded to 2 decimal places. The fastest and slowest cycle times are then identified using the minimum and maximum values, giving a clear overview of the data's typical performance and extremes. A tuple can store fixed, structured data where each position has a clear meaning. In this case, the first element gives the part ID, accessed with zero-based indexing, while the remaining elements give the part's length, width, and height, accessed by taking the slice from the second position to the end. This example shows how Python uses lists and tuples for ordered data. A list stores cycle times that can be updated, while a tuple stores fixed part information that should stay constant. The script reads values by position, adds a new cycle time, calculates the average, and finds the fastest and slowest cycles. Overall, it demonstrates that lists are useful for changing data, while tuples are useful for stable records with fixed meanings. Industrial sequences. In industrial data, the order of information is often just as important as the values themselves. Sequences preserve each item's position, which may represent time, production order, or another meaningful structure. For example, temperature readings or conveyor speed measurements only support useful analysis when their order is maintained, helping reveal trends, behavior, or problems in the process. In industrial engineering, sequences help organize repeated observations, process steps, and related measurements. They are used to track trends, compare planned and actual work, and keep quality data consistent. If the order of data is mismatched across workstations, the results can be misleading, even when the values are correct. Good sequence design must consider both the data itself and what each position represents. Lists and tuples help organize sequence data in industrial work. Lists fit data that changes or grows, such as defect counts or arrival times, while tuples fit fixed records, such as robot coordinates or inspection stages. Choosing the right structure shows whether data is dynamic or stable, making records clearer and easier for teams to share and compare. Python code, industrial sequences. Industrial sequences keep data in a meaningful order. Lists are useful when the collection may grow during operations, while tuples are better for fixed records that should stay the same. Create a list of cycle times in seconds to store the time for each operation in order. The list contains the values 52, 55, 53, 58, and 54, making the data easy to review or update later. A tuple is used to store a part's fixed dimensions in millimeters. Because tuples cannot be changed after they are created, they are a good choice for values that should stay constant. In this case, the three floating point values represent the part's length, width, and thickness. Use zero-based indexing to get the first item in the cycled times list, and negative indexing to get the last item. This lets you quickly access list elements by their position. This update changes the fourth cycle time in the Python list to 56. It shows how lists can be edited directly to correct or refresh stored data. To find the average cycle time, add all the cycle times together, then divide by how many values are in the list. The result is one representative cycle time for the full sequence. The tuple of part dimensions is unpacked into separate variables for length, width, and thickness. This makes each measurement easy to reference later and keeps the code clear when working with a fixed set of related values. The process sums up cycle performance by showing the recorded cycle times, identifying the first and last values, and reporting the average rounded to one decimal place. It then presents the fixed part dimensions, separates them into length, width, and thickness, and displays each measurement clearly. This script shows how lists and tuples can organize industrial data. A list stores cycle times and can be updated, while a tuple stores fixed part dimensions. The script calculates the average cycle time, separates the dimensions for readability, and prints a concise summary including the updated times, first and last values, average time, and part size. Sequence operations. Sequence summary. In industrial engineering, Sequences keep operational data in the correct order, which is essential for accurate interpretation. For data like processing times or sensor readings, changing the order can change the meaning and hide important trends. Treating each value as part of an ordered structure makes it easier to access, update, and summarize information for better decision-making. Sequence operations help turn ordered data into useful information by accessing, updating, and summarizing values by position. Accessing retrieves specific items, updating corrects or revises values in mutable structures, and summarizing finds key results such as counts, totals, maximums, and minimums. Together, these operations support clearer analysis and better decision-making. Sequence summaries connect programming tools to engineering decisions by turning data into useful signals. Measures like minimums, maximums, counts, and totals can reveal issues such as underfilled parts, long waits, missing data, or production performance. Still, these summaries do not show everything, so they should always be interpreted with attention to context, variation, outliers, and data quality. Python code sequence summary. Use ordered production data carefully to summarize sequences and understand patterns. Built-in functions can quickly reveal key sequence information, while lists are useful for data that needs to change, and tuples are better for records that should stay fixed. A list is created to store hourly production data, with 6 integer values representing units produced in each hour. Using a list makes it easy to update individual hourly entries as production data changes. The hour output list is corrected by changing its spurred value to 41. This keeps the dataset aligned with the validated production numbers for later analysis. A tuple is used to store fixed weight inspection limits in grams because its values cannot be changed after creation. This keeps the limits constant throughout the program, making them a dependable reference for checks and comparisons. To summarize the updated production sequence, count the hourly readings, add them to get total output, and find the lowest and highest hourly values. Together, these measures show how many data points were recorded, the total units produced, and the least and most productive hours. To find the average units produced per hour, divide the total units produced by the number of hourly readings. This shows the typical hourly output and uses the reading count as the divisor. The program summarizes hourly production by displaying the output data, the fixed weight limits used for inspection, and the number of readings collected. It then reports key production measures, including the total units made, the lowest and highest hourly outputs, and the average hourly output rounded to 1 decimal place. This script organizes hourly production outputs, corrects one recorded value, and uses fixed weight limits that should not change. It then calculates key statistics, including the number of readings, total production, minimum and maximum output, and the average output per hour with safe division. The result is a concise summary of the production data and its main metrics. Accessing sequence data. Accessing sequence data means retrieving items from an ordered collection, such as a list or tuple, by their position. This is important when order reflects time or process stages, as in industrial readings. Indexing lets you choose specific values, and many languages use zero-based indexing, where the first item is at index 0. Thinking of the index as the number of steps from the start makes this approach easier to understand. Sequences can be accessed one item at a time, or as slices that capture a selected range while keeping the original order. Slices help focus on relevant parts of the data, such as sections of a batch or records after a change. Negative indexing is useful for reaching recent entries in growing sequences like logs, where the latest data often matters most. Accessing sequence data by position requires knowing what each position represents and confirming the data is in the expected order. Using the wrong index or accessing an index that is not present can cause incorrect results and poor decisions. Checking the sequence length and validating positions helps engineers retrieve the right information, track process changes, and make reliable decisions. Python code accessing sequence data. Sequence positions make it easy to access engineering data stored in ordered records like lists and tuples. Indexing retrieves a value by its exact position in the sequence. We create a list to store hourly machine temperature readings in Celsius. Each value is a floating point number, and keeping them in a list makes it easy to access, change, and analyze the readings later. A tuple is used to store the fixed station names in order: cut, drill, inspect, and pack. Because tuples cannot be changed after they are created, they are a good choice for data that should stay constant during the program. Before using items from the temperature list, the code first checks that the list contains at least 3 readings. This prevents the program from trying to access a position that does not exist, which would cause an error. Use indexing to quickly retrieve specific temperature readings from a list. Zero-based indexing gives the first reading at the start of the sequence and the third reading at index 2, while negative indexing lets you access the latest reading directly from the end. We use slicing to take the first 3 hourly machine temperature readings and store them as a new list of startup temperatures. This creates a small subset of the data, useful for examining conditions at the beginning of the process. To summarize the temperature data, calculate the average startup temperature, then identify the highest and lowest recorded values. These basic statistics give a quick overview of the key patterns in the temperature sequence. This example shows how to read values from a tuple of station names. The first item is accessed by its starting position, and the last item is accessed with negative indexing, which avoids needing to know the tuple's length. Because tuples are immutable, reading these values does not change the original data. This section demonstrates basic ways to inspect and summarize stored data. It checks whether there are enough temperature readings, accesses selected temperatures by position, and uses a slice to work with the first 3 readings. It then calculates their average, reports the lowest and highest temperatures, and shows how to read the first and last station names from a tuple without changing it. This script shows basic Python sequence operations using a list of hourly machine temperatures and a tuple of station names. It first checks that enough temperature readings are available, then uses indexing to access selected readings and slicing to capture the first 3 as a startup window. It summarizes the data by calculating the startup average, finding the lowest and highest temperatures, and retrieving the first and last station names. The printed results provide a compact overview of the sequence data and how lists and tuples can be accessed and analyzed. Sequence summaries. Sequence summaries give industrial engineers a quick overview of ordered data by showing essentials such as count, minimum and maximum values, totals, and typical values. They help check data completeness, spot performance extremes, and estimate outputs like labor hours or production units. These summaries do not replace deeper analysis, but they quickly indicate where further investigation is needed. When summarizing sequence data, choose measures that match the context and data type. Maximum and minimum values can reveal bottlenecks, ideal conditions, or possible errors, like totals and counts, can show quality loss or how many observations were recorded. Built-in summary functions support consistency, but the method should fit the data, such as summing numeric volumes and counting non-numeric records. Effective sequence summaries depend on checking that the data covers the right time period, is correctly ordered, and includes any needed updates or corrections. Lists may change as data is added or fixed, while tuples often represent stable records, such as design parameters. Good summarization highlights key insights, such as counts or averages, while still allowing engineers to examine the full data when needed. Python code, sequence summaries. Summaries turn ordered data into practical decisions. Industrial engineers often use them to interpret sequences of observations, and built-in functions can provide quick insight for operations. We create an ordered list of cycle times measured in seconds, keeping the observations in their original sequence. This makes it possible to analyze the data, such as calculating averages and finding the fastest or slowest times. Use the length function on the cycle time list to find the total number of observations. This count is needed for later calculations, such as computing the average cycle time. Use the minimum function to find the fastest cycle time, since it returns the smallest observation. Use the maximum function to find the slowest cycle time, since it returns the largest observation. Together, these functions quickly show the range of cycle times in the data. To find the total processing time, add together all recorded cycle times. The result is one cumulative value that shows the overall time spent on the process. Typical cycle time is found by adding the times from all observed cycles and dividing by the number of observations. This average gives a simple central measure of how long a cycle usually takes, smoothing out differences among individual observations. This summary reports key statistics for the cycle time data: the number of observations, the fastest and slowest recorded times, the total time across all cycles, and the average cycle time rounded to one decimal place. Together, these values give a quick overview of dataset size, performance range, overall duration, and a typical cycle length. A tuple is used to store approved standard batch sizes as fixed, unchangeable values, which helps protect their integrity. The sum function then adds these values together to give the total approved units, providing a quick view of the overall scale of operations. To summarize the approved batch sizes, use the length function to count how many batch entries are in the tuple. Then display the previously calculated total to show the overall number of approved units. Together, these two values give a quick summary of the approved batch data. This script summarizes operational cycle time data by counting observations, finding the fastest and slowest times, and calculating the total and average time, with the average rounded for readability. It also totals a set of approved batch sizes to show the overall number of units. The printed results give a quick, practical overview of performance and approved production quantities for industrial engineering analysis. Engineering sequence choices. Mutable records. Mutable records are useful when engineering sequences must change as work evolves or new data appears. A mutable list lets teams add, remove, or reorder items without rebuilding the whole record. This helps maintenance and production plans stay current with shifting priorities and supports better real-time decisions. Mutable records are useful when information needs to change throughout the day, such as orders or work schedules in an industrial setting. They support real-time operations, but they can also create confusion if multiple people use or edit the same data at once. To prevent discrepancies, these records need clear ownership, documentation, and coordination, so everyone works from the same understanding. Mutable records are useful for representing the current state of a process that changes often, such as production schedules, logistics plans, or evolving simulation experiments. They make updates easy, but they can make past states harder to trace. Use them for dynamic work and record important milestones separately when you need stability or history. Python code, mutable records. Model records can be listed when they change, which is important in industrial queues where updates are often needed. Supporting mutability helps these systems respond to live operational decisions. We create a mutable inspection queue to store the machines scheduled for inspection. It starts with Pump 1, Conveyor 2, and Mixer 3, and can be updated as inspection needs change. We start by showing the current inspection queue, which lists the machines waiting to be checked. This gives a quick view of pending inspection tasks and supports basic workflow tracking. This code adds an urgent machine, press 9, near the front of the inspection queue. It uses the insert method to place the item at a specific position, so it can be handled before lower priority machines. This shows how a queue can be adjusted dynamically when task urgency changes. This code updates the inspection queue by changing the first machine entry to Pump-1A. The change keeps the queue aligned with the machine's current designation or operational status. The pop method removes a task from the inspection queue in a specific position and returns that task at the same time. This lets the completed task be saved for tracking, logging, or further processing. This code adds a newly reported machine, Robot 4, to the inspection queue using the append list method. Append places the new item at the end of the list, so it will be inspected after the current tasks. This keeps the queue updated as new inspection needs arise. After a task is completed and removed from the inspection queue, we print it and show the updated queue of remaining tasks. We then check the first task in line to see what should be handled next and count how many tasks are still waiting. This keeps the inspection schedule clear and up to date. A tuple is being used to store a fixed route made up of Dock A, Aisle 3, and Pack 2. Because tuples cannot be changed after they are created, they are useful for information that should stay constant, such as stable process steps, records, or configurations. Tuples are useful for storing stable historical records because they are immutable and cannot be changed over time. In this case, the code displays an approved route from a tuple, showing how tuples help keep fixed information reliable and consistent, compared with mutable data structures. This example shows how a mutable list can manage an inspection schedule that changes in real time. Tasks can be added, updated, removed, and counted as the schedule evolves, making lists useful for live operational work. It contrasts this with an immutable tuple, which represents a fixed, approved route and is better suited for information that should not change. Immutable records. In Python, immutable records such as tuples store ordered data that cannot be changed after creation. This helps protect fixed information in industrial engineering, such as machine coordinates, batch identifiers, calibration constants, or inspection results. By preventing accidental edits, immutable records support data integrity, traceability, and consistent ordering of important values. Using immutable records such as tuples shows that data is intended to remain unchanged. This makes multi-step workflows clearer and helps protect original values while separate calculations are performed. Keeping raw data intact supports data integrity, which is important for reliable decisions and compliance checks. Immutable sequences are useful when records must be shared or used as stable identifiers, such as workstation numbers or product variants. In industrial systems, immutability helps keep identity consistent across scheduling, inventory, and other processes. When changes are needed, create a new sequence instead of altering the original, supporting clear versioning, accountability, and reliable data over time. Python code. Immutable records. Use tuples for stable engineering records that should not change, and use lists for records that need editing. The key choice is whether the data should remain fixed or be updated over time. A machine's location can be stored as an immutable tuple containing 3 floating point coordinates in feet. Using a tuple helps ensure the location stays fixed during the program, preventing accidental changes when it represents a stable reference point. A Python list is used to store daily production counts, with each integer representing 1 day's output. Because lists are mutable, the counts can be updated later as new production data becomes available. A machine's location can be stored as a tuple, which means its values cannot be changed after creation. Printing the tuple shows the machine's fixed position and helps keep the location records stable and reliable. This shows the current daily production counts. Because the list is mutable, its values can be updated as production changes each day. Printing it gives a quick snapshot of the latest production data for review. Changing the third value in the production counts list shows that lists are mutable. By updating the item at index 2 to 120, we directly change the count for that day, making lists useful for data that may need to be revised over time. To find the average updated daily production count, add all the daily counts together and divide by the number of days. This gives a single summary value for the updated sequence. To update a machine location stored in a tuple, we create a new tuple with the revised values instead of changing the original. This works because tuples are immutable, meaning their contents cannot be modified directly. Keeping the original unchanged preserves reliable data, while the new tuple records the update. The output first shows the updated daily production counts, then displays their average rounded to 1 decimal place. It also prints the original machine location tuple to show that it has not changed. A separate revised tuple is printed for the updated location, demonstrating that tuples are immutable and must be replaced rather than modified. A try-except block can demonstrate that tuples cannot be changed. When the code tries to modify an element in the tuple, Python raises a type error, and the error handler reports that the edit was blocked. This shows how tuple immutability helps prevent accidental changes and protect data integrity. A tuple is used to store fixed identification details for a batch, such as the production line, shift, and part number. Because tuples cannot be changed, they provide a stable way to keep related identifiers grouped together throughout the program. The code prints a stable batch identifier stored as a tuple. This tuple combines fields such as the production line, shift, and part number. And because it is immutable, the identifier cannot be accidentally changed. This makes it a reliable way to refer to that specific batch throughout the program. This script shows when to use tuples and lists in Python. Tuples are used for fixed data, such as a machine location or batch key, because they cannot be changed after creation. Lists are used for data that needs updates, such as daily production counts, which can be modified before calculating an average. The example also shows that changing a tuple requires creating a new one, and attempting to edit the original causes a type error. Stable sequence records. Stable sequence records keep data in a fixed order, which is essential for integrity, traceability, and accountability in engineering. Their value comes not only from the data itself, but from the exact order in which fields and events were recorded. Once entered, they should not be changed because they support audits, compliance checks, and evidence of completed events in areas like manufacturing and logistics. For records that represent fixed observations or finalized configurations, a stable, immutable sequence helps keep related values together and unchanged. After validation, this makes calculations and data processing more reliable by preventing accidental modifications. It is especially useful for finalized records like batch summaries, maintenance logs, or shipment details, where later steps must trust that the record's structure and meaning remain consistent. Stable sequence records separate data that is still being planned from data that must be preserved. A production schedule may change during a shift, but once the shift ends, the final job order becomes a historical record. It should not be edited directly. Corrections should be made through new records or amendments. This approach supports transparency, accountability, and responsible technical record keeping. Python code. Stable sequence records. Use stable records to protect finalized engineering data. Tuples are best when field order and values must stay fixed, while lists are better for data that still needs active updates. A finalized inspection record is stored as a tuple, so its values cannot be changed after creation. It contains the part identifier, station identifier, diameter measurement in inches, and result status. This fixed structure helps preserve the order and integrity of finalized engineering data. An active jobs list stores tasks such as cutting, drilling, inspecting, and packing. Because lists are mutable, their contents can be changed, making them useful for tracking tasks that are in progress or need updates. This code updates a list of active jobs by changing the second item from drill to ream. It shows that lists can be modified after they are created, unlike tuples, which cannot. This makes lists useful when data needs to change dynamically, such as in planning or scheduling. The inspection record tuple is unpacked into separate meaningful values for the part ID, station ID, diameter, and result. This makes each piece of data easier to access and keeps the code clearer than using position numbers. This example tries to change an element inside a Python tuple, but tuples are immutable, so their contents cannot be changed after creation. The attempt raises a type error, which is handled by the exception block. This shows how tuples help protect data integrity by preventing accidental modification. This code handles the error that occurs when trying to change a tuple. Because tuples cannot be modified, the attempted change raises a type error. Catching that error confirms the tuple protected its contents, and the resulting message can later explain this immutability to the user. We create a new tuple using the existing part identifier, station identifier, and result, while changing the diameter to 2.499. This updates the inspection data without altering the original tuple, preserving tuple immutability. The output shows how tuples support stable, structured inspection data. It prints the finalized tuple, the updated active jobs list, and a diameter value taken from the record. It also demonstrates that tuples prevent accidental changes, while a revised tuple can be created deliberately to update one field. Finally, printing the tuple length reinforces that the inspection record has a fixed number of fields. This script shows how tuples and lists handle engineering data differently. A tuple stores a finalized inspection record that cannot be changed, and an attempted edit raises an error that confirms its immutability. A list is used for active jobs because it can be updated as work changes. The script also unpacks the tuple, creates a revised tuple when a value needs to change, and checks the tuple length to emphasize its fixed structure. In this lecture, you learn to create lists and tuples that represent ordered industrial engineering data, access, update, and summarize sequence data using indexing and built-in functions, and choose between mutable and immutable sequences for appropriate engineering records. In the next lecture, Lecture B, we will go over dictionaries and sets.
Thank you for your attention. See you all in the next lecture.